Welcome to AP Calculus. This is the first set of videos we'll be doing, learning about Unit 1, Limits, Continuity, and the Squeeze Theorem. If I look at this graph, I might want to know what's the slope of the curve at x equals 2. So this point right here, what's the slope of the curve? Right now, I don't know how to do that. I know that when x is 2, it looks like my y is 0. But that doesn't really tell me anything about my slope. And that's the reason we're going to learn about limits. We're going to find out, using limits, what the slope of the curve is at that point. One way we can estimate that line, the slope of that curve, is by finding the slope of the lines near the point. So let's say we draw that line, and maybe this line, and maybe this line, and maybe this line. So hopefully you can see that the red dots are getting closer and closer and closer to the blue dot. So let's take a look at the first ones that we looked at, the first ones we drew. The blue dot and the red dot. If I want to find the slope of the line between the blue dot and the red dot, my slope is going to be y2 minus y1 over x2 minus x1. I'm sure everyone's seen slope before. This is just the standard slope formula. We'll see it in a lot of different ways, but this is the way that you're most used to seeing it since at least freshman year. Now, as these dots get very close to the blue dot, the slope of the line is getting closer and closer to this line called the tangent line. I know we spoke about the tangent line last year at the end of the year, but we're going to talk a lot more about it now. I should mention here that these lines are called the secant lines. So these lines that go through the line at the point and another point are called secants. On this slide, we have the same picture of our graph. This time they're going to say our C is 2, that's our blue dot, and then the X is whatever's moving close to it. For example, to start, our X looks like it's about 3. Now, as that 3 gets closer and closer and closer and closer and closer to 2, we're able to find the slope of the tangent line. This is super important in calculus. This is our first big concept we're going to go over. The derivative is the slope of the tangent line. So we need to start talking about the tangent line. I know you haven't learned the word derivative yet, but slope of the tangent line is where it all starts. So as we talked about on the previous slide, we were making secant lines, and now we're taking the limit of those secant lines to get the tangent line. So we're taking each one of those secant lines and bringing it really close to the number 2, or to x equals c, to make it so that we get one straight line that touches the graph in only one point. Here we have an animation showing how the secant line becomes the tangent line.
Makes a secant line a tangent line. As you can see, AB is a secant line, and that as I drag A toward B, the secant line becomes a tangent line. What I want you to observe is the value h. As h goes to 0, the secant line becomes the tangent line, and therefore this should help you understand the limit formula. As h goes to 0, the secant line becomes a tangent line.
Now, I realize some of that with the limit formula and h were a little over your head for the moment. Have no fear, we'll get there eventually. But I thought that a demonstration of the A coming close to the B and making one straight line was pretty instructive. All right, let's walk through our first example from a book problem. And all the examples that I'm going to do, they're all from the book, and I have the page number listed, so feel free to follow along in the book as we talk. This first one says, in words, explain what does this whole long expression here mean. So what does that mean? I'll give you a second to think about it. All right, so what it says in words is the limit as x approaches -1 of the function x squared minus 1 over x plus 1 is -2. So this piece in words says the limit as x approaches -1, and then that's the function that we're going to talk about, is equals -2. So now for example 2, let's investigate using a table. There are a lot of ways to make a table. We're going to do it on the graphing calculator. You can just plug it in, 2x plus 5, and plug in all the different numbers that we see. The other way to do it is to put 2x plus 5 into the y equals, and then from there you can just use the y value button on your graphing function, and we can trace each number. So for example, I'm going to trace equals 1.99, and I get 8.98. 1.999, and I'll get 8.898, 1.999, 8.998. Oops, I'm supposed to have 119 for that one, 1.999. That was 998. Now let's do the other side. 2.00001, 9.0002, 2.001, 9.002, 2.01, 9.02. Now I didn't mention it, but it's worth mentioning. These numbers are getting close to 2. So I'm getting close to 2 on either direction, the numbers that are a little bit smaller and the numbers that are a little bit bigger. And I want to know what happens to the function. As my x gets close to 2, what does my y value get close to? And hopefully you can see here that we're getting very close to 9 from the left and from the right. So the numbers that are smaller than 2 approach 9, and the numbers that are bigger than 2 approach 9. So I could say that my limit as x approaches 2 of 2x plus 5 is 9. Here's a formal way to say what I just said in the last slide. The limit as x goes to c from the left is the limit from the left. That's as x approaches c from the left, the limit is L. And the limit as x approaches c from the right, f of x equals L from the right. The limit as x approaches c from the right is L. Now let's delve a little bit more into these symbols. So this negative symbol up here means from the left, and this positive symbol up here means from the right. Now this is super important. In order for a limit to exist, the limit from the left has to be the same as the limit from the right. So in our previous slide, we saw that both the numbers less than 2 and the numbers greater than 2 approached the number 9. So our limit was 9. If they did not approach the same number, then our limit does not exist. So let's take a look at the graph of 3x plus 1. In this case, we're being asked to find the limit as x approaches 2 of a piecewise function. They're telling us that the graph is 3x plus 1 when x does not equal 2, and when x equals 2, the graph is 10. So I sketched this graph of the function that they're explaining, and notice there's this hole. And when we have this hole, it means that the function doesn't exist at that point. So all of these other values are real and valuable for this 3x plus 1 or for this function. But when x is 2, we jump all the way up here to be 10. Now we're going to examine what happens at the limit. So the limit as x approaches 2, I'm going to have to look at from each direction, from the left and from the right. So from the left, it looks like, from the left, as x approaches 2, the function approaches 7. And from the right, as x approaches 2, the function also approaches 7. So overall, the limit as x approaches 2 of the function is 7. Now this is a really, really, really important point that I've made a lot last year, but I don't know if you remember it. A limit does not care what happens at the point. A limit only cares what happens near the point. So near the point, the function is approaching 7 from both the left and the right. And at the point, the function equals 10. And that's okay that those things are completely different. Let's look at another limit. As x approaches 0 of the function f of x, again we have a piecewise function. When x is less than 0, we have the function f of x equals x, so this y equals x line. And then when x is greater than 0, we have y equals 1, this horizontal line here. Notice they're both open circles because we don't have an equals to anywhere in our explanation. So as I go from the left, let's see what happens. The limit as x goes to 0 from the left of f of x, it looks like our function approaches 0. And as I go from the right, the limit as x goes to 0 from the right of f of x, it looks like our y approaches 1. These are not the same values, so the limit as x goes to 0 of f of x does not exist. Again, we have to approach the same number from the left and from the right in order for the limit of our function to exist.